Why does breaking a connecting rod make it more precise? It sounds insane, but this is one of the most advanced processes inside a modern engine. The big end of the rod has to match the crankshaft with absolute accuracy. If the two halves shift even slightly, the crank journal gets scratched. Friction shoots up, lubrication fails, and the engine's life drops fast. The old method was simple cutting, but smooth cuts slip. They move, they do not hold. Fracture splitting works completely differently. A micro-stress groove is cut inside the big end, and when the rod is forced open, it cracks along that groove, creating a rough 3D surface that is completely unique, almost like a metal fingerprint. Those rough edges are the key. When the cap goes back on, the surfaces lock together instantly, with no sliding or shifting, just a tight and rock-solid fit. At more than 10,000 RPM, this natural lock keeps the rod exactly where it needs to be. Without fracture splitting, you would need far more expensive and far more complicated machining to reach the. Look closely at this process. This is not someone assembling a tiny toy. It is a worker installing the magnetic core of a heavy-duty industrial system. These T-shaped magnets may look small, but they control high-speed field stability and determine whether the entire machine can run under load. You might think the worker is just tapping pieces into place, but every magnet requires micro-level precision. The direction, the angle, and the spacing cannot be off by even a fraction of tolerance. If one piece shifts, the entire magnetic field goes out of balance instantly. The tighter and cleaner the alignment is, the more concentrated and efficient the magnetic output becomes. That prevents overheating and energy loss, and it is something no automated tool can match. Every magnet has to be positioned and verified by hand. But if even one piece fails to seat correctly, the magnetic field will scatter at high speed, and the whole system can shake itself apart. Only after all magnets lock into perfect alignment can the metal housing be sealed, turning simple rotation into a stable industrial-grade magnetic output. In the end, these tiny components most people overlook are exactly what protect the machine's power, safety, and lifespan. Why do mixer drivers fear concrete hardening inside the drum? Because it means the entire drum can turn into a giant rock, and they're the ones who have to deal with it. It is the worst problem a mixer truck can have. The worker has to crawl in through the small opening at the back, squeeze into the tight metal drum, and break off those rock-hard chunks of concrete one piece at a time. This happens when the concrete isn't poured out in time, or the drum stops spinning for too long, causing the mix to set and eventually freeze the whole drum so it can't move at all. The cost climbs fast depending on how bad it is. Light buildup might cost a few dozen to over $100. A moderate drum freeze is charged by weight, usually about $100 per ton. A severe freeze can reach $3,000. And if the concrete gets so hard that the drum must be cut open, you'll also pay extra for welding and repairs. Replacing the entire drum, on the other hand, costs around $40,000. So here's the question. When a mixer drum can freeze up at any moment, would you pay to clean it out, or would you just replace it? Do those electric turbo boosters online really work? They seem legit, but let's start with how a real turbo actually works. A traditional turbo uses exhaust gas to spin a turbine wheel, which turns a compressor on the other side. That compressor pushes more air into the engine, and more air means more power. But here's the catch. A turbo only builds boost once there's enough exhaust flow, and until then, you wait. That delay is the turbo lag everyone talks about. To fix that, automakers added something new, an electric assist turbo. A small electric motor drives an electric compressor, giving the engine a little boost at low RPM. That small push is enough to wake the turbo up sooner, so the engine makes strong torque even at low speed. Turbo lag almost disappears. And those electric turbos you see online, they look cool, but inside they're usually just a tiny motor spinning a plastic fan. Sure, they move a bit more air, but nothing close to real boost. At the end of the day, they're not turbochargers. They're just noisy. Why does this rope cost $1.5 million? It may look thin, but it can stop a heavy fighter jet in 3 seconds. It's called an arresting cable, known as the lifeline of an aircraft carrier. So why is it important? Because a carrier's runway is only about 1,000 feet long, nowhere near enough for a jet to slow down on its own, which is why 4 arresting cables are stretched across the rear of the deck. When a fighter lands, its tail hook grabs the cable, and the massive impact is instantly transferred to the energy-absorbing system, bringing the jet to a full stop in an extremely short distance. Handling that force is no simple task, so each cable is built from the most durable and expensive materials. 30 steel wires twisted into one strand, and 6 strands twisted into a single cable. One cable is strong enough to stop 3 jets at once without snapping, and that's exactly why it costs so much. And during takeoff, steam or electromagnetic catapults launch the jet to about 190 miles per hour in just 2 seconds. These two systems together form the true lifeline of an aircraft carrier. What's that long tail behind this weird shit used for? This is a seismic survey vessel. It uses a device similar to a giant air gun to shoot high-pressure air into the water, creating low-frequency waves powerful enough to penetrate the seafloor. And whenever they hit a different formation, part of the energy bounces back toward the surface. Oil-bearing layers have lower density, so their echoes are much easier to recognize. And those long lines trailing behind the ship aren't regular cables. They are data streamers stretching nearly 7 miles, each packed with highly sensitive hydrophones designed to capture even the faintest signals coming from deep below the seabed. By measuring the return time and strength of each wave, scientists can rebuild a full 3D image of the sea floor and determine whether oil or gas might be hidden underneath. But this system isn't perfect. The powerful sound pulses can disturb whales and other marine animals. So in certain regions, the ship must stop and let them pass. Even so, in the dark depths where human eyes see nothing, this vessel remains the sharpest ear we have. You might think these massive gas pipelines are welded by hand, but most of the work is done by machines to ensure 2 giant steel pipes fit together perfectly. The process starts with a beveling machine. It cuts the pipe ends at a precise angle, allowing molten metal to fully penetrate and fuse the joint during welding. Next comes the automatic internal welder. It crawls slowly through the narrow pipe, aligning both ends with incredible precision and laying the first internal weld, the foundation of the entire connection. Then, a crane lowers a large welding shelter over the joint. Inside is a track-mounted automatic welder, essentially a mobile cleanroom that blocks wind, dust, and moisture, ensuring the weld isn't oxidized or cracked. Once everything is ready, the machine begins to rotate. Its torch moves smoothly along the track, creating a continuous 360-degree weld that fuses the 2 steel giants into one seamless line. What looks like cold mechanical motion is actually the lifeline of global energy stretching for thousands of miles. So here's the question: if the machines are doing all the work, does that mean this is definitely genius mechanical designs? This ring may look ordinary, but inside it hides a mechanism that completely changes how stuck fasteners are removed. When tightened, it works like a normal washer, simply spreading the load, but its real magic appears during removal. In factories and heavy machinery, bolts and nuts endure huge pressure and constant vibration, and over time the threads can seize so badly that even heavy tools cannot break them free. What makes this mechanical load release washer special is the small internal structure designed to release that force automatically. When you turn the nut counterclockwise by about 12 degrees, the mechanism inside shifts. The locking piece slips into a preset recess, and the axial clamping force on the threads collapses instantly. Once that preload disappears, the friction that made the nut seize up vanishes with it, and the nut suddenly spins free, almost like it was never tightened at all. A stuck nut solved with a single twist. This might be one of the smartest little mechanical designs ever made. This is definitely one of the most dangerous jobs in the world. One wrong move, and you could be buried alive. At the bottom of that massive sand pile lies a narrow chute that carries sand out of the barge. But here's the problem. The sand is packed so tightly and weighs so much that it often refuses to move, so the workers have to do it by hand, loosening it bit by bit. Every strike, every shove, is a battle against gravity itself. The smartest part of the system is hidden underneath. Before loading, workers lay down wooden planks across the chute. These planks act like small gates, controlling the flow of sand. When unloading begins, they pull the boards out one by one, allowing the sand to slide slowly instead of collapsing all at once. This prevents blockages and overloads and gives them a narrow, stable platform to stand on. There are no machines here, no buttons to press, just experience, instinct, and perfect balance. They work while the ground beneath them could give way at any second. So let me ask you, would you dare to stand there? Can you believe this? This piece of wood is actually made of concrete. It can sit outdoors for decades without cracking or rotting, all thanks to a technique called Folks Wood Concrete, a way of recreating wood using stone. First, workers prepare special molds that capture every detail of real wood, the grain, the rings, even tiny cracks. Then they spray a thin layer of mineral paint inside the mold, which gives the final piece its realistic color and texture. Next, they pour in the concrete while adding a steel cage or wire mesh to keep it strong. Once it hardens, the mold is carefully removed, revealing what looks like a wooden beam growing straight out of stone. In some parks and scenic areas, craftsmen skip the molds altogether. Using just steel bars, mortar, and carving tools, they hand-shape the texture before it dries. After the mortar fully hardens, these concrete wood pieces can stand strong through decades of wind and rain, harder, tougher, and longer lasting than real timber. It may look like wood, but it's really a mass. If a helicopter crashes into the ocean, how do the pilots escape? The truth is, American Marine aviators have trained for this exact moment countless times. It's called the Underwater Helicopter Escape Course. The training takes place in a pool about 15 feet deep, using an 18-foot-long mock helicopter cabin. A hydraulic system flips the cabin 180 degrees underwater, plunging trainees into total darkness and disorientation. Within 5 to 8 seconds, they must unbuckle their harness, find the reference point, locate the exit, and swim free. Hesitate, and the bubbles might be the only light you see. Next comes 6 full rounds of drills, each simulating inverted or obstructed conditions. Every round is timed at 30 seconds. Fail once, and you repeat. They wear a short-term STAS oxygen unit. The hardest part isn't strength, it's control. They must move before panic sets in, training their bodies to react faster than their minds. The pass rate is about 85%, but the goal is simple: build muscle memory strong enough to survive the real thing. Once they reach the surface, they fire a smoke signal and wait for the... Why are they throwing life rafts off an aircraft carrier? This isn't an accident. It's part of American Navy escape training. When the order is given, sailors must jump straight from decks over 100 feet high into the open sea. It's one of the most dangerous drills they face. Sometimes sharks appear nearby, so they have to climb onto the inflatable raft as fast as possible. These rafts can inflate automatically in just a few seconds. Once they hit the water, they unfold into floating shelters that stay stable even in rough waves. Every move has to be precise. One mistake could be fatal. Unlike traditional lifeboats, they need no manual setup and deploy much faster. One person can evacuate every 3 seconds, allowing hundreds to escape within minutes. Inside, there's food, drinking water, first aid kits, and communication gear enough to keep sailors alive for days until rescue teams arrive. Out on the ocean, every launch and every jump could mean life or death. So here's the question: would you trust your life to an inflatable raft like this? This pipeline thrown into the ocean isn't for oil or gas. It's actually an undersea cable, and it's the reason your online games don't lag. You can thank this cable for that. What looks like a pipe is actually made of multiple protective layers. At its core lies glass fiber that carries light signal, transferring data between continents. Around it are layers of armor built to withstand deep sea pressure, strong enough to resist even a shark's bite. The installation process is just as impressive. Special cable-laying ships slowly unroll it from giant spools across the ocean floor. But the closer it gets to shore, the trickier it gets. Engineers use underwater plows to bury the cable beneath the sand so it won't get cut by anchors or torn by fishing nets. So why go through all this trouble? Because fiber optic cables are lightning fast and incredibly stable. The downside? They're insanely expensive, costing between $30,000 and $80,000 per mile. That means a single project can reach billions of dollars. So here's the question: spending billions just to make your internet a few milliseconds faster. Why do lifeboats drop straight from 10 stories into the sea? It sounds like an accident, but it's actually the design. This free-fall lifeboat hits the water in just 3 seconds, faster than any other escape method. But why take that risk? Because when a ship catches fire, explodes, or starts to tip, a few extra seconds could mean losing the entire vessel. Still, can dropping like that really be safe? The impact feels like crashing into concrete. So engineers came up with a brutal solution: make it fully sealed, fireproof, smokeproof, and shock-absorbing. When it hits the water, even if a giant wave flips it, the boat rolls itself upright. Why not use ropes instead? They tried, but in heavy seas, ropes can snap without warning. So they switched to the Just Drop design. Crazy at first glance, but far safer in reality. 3 seconds of free fall for one chance to live. It's not recklessness, it's survival engineering. And yes, some places let you try it for fun, about $100 a ride. Would you dare? Can you believe this machine can make over $3 million a year? It's called a horizontal directional drilling rig. Once you send the drill head underground, it can bore a tunnel beneath the surface without leaving a single trace above ground. To put it in perspective, a construction crew burying pipes by hand can only manage about 200 feet a day. But this machine can drill through more than 1,600 feet of soil in the same amount of time. That's why operators using it can easily make millions a year. So how does it work? Inside the drill head is a guidance system. As it spins and digs forward, it sends wireless signals to the surface. Workers track it in real time using a receiver, while the operator fine-tunes the angle with a control stick to keep the tunnel perfectly aligned. Once the drill breaks through to the exit point, they attach a larger reamer, and the rig starts pulling back, dragging the connected pipeline right through the underground path. But it's not flawless. A full-size rig can cost over $400,000, and precision is everything just a few degrees off, and the entire tunnel could be ruined. So here's the real question: would you spend $400,000 on one